Hey algebras! Today we're excited to talk about the graphs of logs. So we're going to learn how to graph logarithmic equations. We're going to use those same familiar transformations. But first let's talk about the relationship between an exponential equation. Remember that's where we have an exponent with that variable in it. And then our log equation, which of course we know is the inverse. So it's important to look at the characteristics of each of these graphs and talk about how they are opposites in every way. Okay, so first we'll talk about our exponential graph. And it's always good to consider a table of input-output values. So I know we can type it into the calculator, but let's think about it first. An exponent can be positive, negative, or 0. So if I put 0 in, anything to the 0 power is 1, 10 to the first power, and 10 squared. Don't forget that when I have a negative exponent, that means I'm dividing. So that makes this 1/10, and thus makes this 1/100th. And we can see an interesting story here where I know that anything to the 0 power is 1, an input of 0 gives us an output of 1, and an input of 1 gives us an output of 10. An input of negative 1 is 1/10. An input of negative 2 is 1/100th. Now, it's so hard to draw all of these values because I know that they approach our x-axis and never quite reach it. And just we're bound to the limits of what we can draw. So when we draw an exponential curve, it's got that huge part of growth, but then it reaches that x-axis. If we go ahead and put this into the graphing calculator, we can go ahead and say this is 10 to the x. Look at the graph, and we can see how it curves down, and it gets so close you can barely even tell that it's separate from the axis. When you look at the table of values, we'll go ahead and go all the way back to starting at 0. But we can see this cool pattern. Notice once we run out of decimal places, we go to scientific notation. That's what that E means. That's 1 times 10 to the 6th. As I go up into negative exponents, notice my values are not negative, but they're just getting closer and closer and closer to 0. And that's where we have that idea of an asymptote. It's getting closer to, but it's never going to reach 0. Notice this is a negative exponent. It's not a negative value. This is 1 times 10 to the negative 4th. We run out of spaces, so it becomes easier for the calculator to use scientific notation. Those negative exponents mean small, small, small numbers. All right, let's talk about the log side of the story. When we have logs, remember these are inverses. So what's interesting is we can talk about our x and y table, but in reality, this is a switch, the exact opposite of this. And if I write this in exponential form, you can see. So we know that this is log base 10. It's the common log. So I have 10 to the y is equal to x. That's that value that we have as a result. So what's interesting is I'm going to do the same thing where I have my input values for my y. And you can see these same input values, negative 2, negative 1, 0, 1, and 2. When I put them in, I get those same values out for y. But remember, it's not really y, it's our x, it's our output, because our x here is the output of this exponential equation. This log equation has the exponent as the output. Okay, so if I put negative 2 in for y, that still gives me my fraction of 1/100th, 1/10. Anything to the 0 power is 1, 10 to the first power, and 10 squared. So as an inverse, we can see how the log and the exponential equation are the swaps of each other. So when we go to graph this, it'll feel backwards, but you go over 1 and up 0. Now that corresponds to this over 0 up 1 point that we know from exponential. So we can go over 10 and up 1. We can go over 1/10 and down 1. We can go over 1/100th and down 2. So instead of our graph snuggling up to the x-axis, our log graph snuggles up to the y. Now, if I were to put a dotted line on the linear parent function of y is equal to x, if I were to put, then you can see how these two graphs are inverses because they are reflections of each other over that x is equal to y line. Okay, let's start talking about some of their properties. So when I look through and I look at these properties of our parent, exponent, and log graph, go ahead and take a minute and you fill them in and we'll come back and compare answers. Okay, so let's talk about these and see how you did. And in your mind, I really want you to think about how are these two opposites in every way. Let's first just start with a conversation about domain and range. So when we look here, our domain, anything can go in to this function. I can have a negative input, I can have a positive input, anything can go in. But when we look at our input and output of our log function, it's anything can come out because our domain is actually limited. I'm not going to have any negative input x values, and that's because I'm not going to have the output of an exponential function be negative. So this is a big idea about what this value here can and cannot be. We can't have it equal to 0, and we can't have it equal to a negative value, because that doesn't ever happen in an exponential function. I don't get an output that's negative, and I don't get an output of 0. So when I'm trying to find the exponent of a certain base that gives me this outcome, guess what? There's no negatives in here. So our domain snuggles up to, but is never quite equal to 0, all the way up to infinity. And that models our output. So if you see here how these are all crisscross, you can understand that inverse relationship. Okay, my asymptotes for an exponential function are going to be this horizontal line that approaches. My asymptote for that logarithmic function is going to be this vertical line at x is equal to 0. When we talk about where is this graph increasing, it's increasing for the entire part of the graph. It's never decreasing, but check out, remember our intervals are a conversation of x's. I can have x's from negative infinity to positive infinity. That's why that's here. Here, my x's are limited. So these two answers are going to be related. I can only have an interval described by what my possible input values are. All right, so when we keep in mind this idea about them being opposites, here we go again with the intercepts. Each of these do not ever cross that axis that represents their asymptote. So this is never going to cross my y-axis, so I'm not going to have a y-intercept. This is never going to cross my x-axis, so no x-intercept. Remember when we talk about zeros, that's our conversation about x-intercepts. Here we have an x-intercept on our log graph, just the same as we have a y-intercept. So that idea of opposites still is pretty important. All right, so when we talk about end behavior, remember this is a conversation about end behavior. Where is this graph going? That's what we like to ask ourselves. As my exponential graph goes to negative infinity, it's going to approach 0. as it goes to positive infinity, it's going to approach infinity. So we have those two answers there. Now notice when we talk about x approaching positive infinity, we can have that conversation. Where's this graph going? It's going to take a long time to get there, but it is eventually going to get higher and higher and higher. But notice we can't have a conversation about x approaching negative infinity because that's not ever happening. It's never going to cross our asymptote. All right, so here we have some similarities and differences between exponents and logarithms. So go ahead and say what you think, and then we'll compare notes in a minute. Go ahead. Okay, so here's some of the ones that I came up with. They both have asymptotes, but one is horizontal, one's vertical. They both only have one intercept, but our exponential equations intercept the y-axis and our logarithmic intercept the x. They are both always increasing, and they are both curved graphs. Our logarithmic graph doesn't have an end behavior for when x approaches negative infinity. Hey, if you have other ones, make sure that you bring them to class because I'd love to hear your thoughts on any other differences that you found between exponential and logarithmic graphs. Okay, let's pop over to the next side. Okay, so here we have something that should look very familiar to you because we've seen this A out in the front before. We've seen this H in with the X before. We've seen this K being added or subtracted before. So if you look at each of these three familiar friends, we can talk about what they're going to do to our log graph. Now, something to make sure you know, that this here is always going to be our base, and it is not part of our transformation, so we don't need to worry about that. All right, so go ahead and take a minute and fill in what you know about what impact A, H, and K have on our graph, and then check back in for your answers. All right, so let's go ahead and review this. We can have a stretch or a compression or a reflection thanks to A. So remember that reflection happens when A is negative, and we need to know that it's going to reflect over our x-axis. Our stretch and our compression depend upon that value. So if the absolute value of A is greater than 1, it's a stretch. It's a compression if the absolute value of A is greater than 0 but less than 1. Any one of those fraction values will give us that. H is going to make our graph move left and right. And remember, this is a naturally negative situation. So if you see a plus sign here, then that means that H has a negative value. So keep that in mind. It's not true to sign, it's opposite. K is our vertical shift, up and down, and that one is true to sign. When we talk about our domain, we can only put in from that vertical asymptote on. So it might be a good idea for you to picture what that graph looks like, because that vertical asymptote comes up and goes something like this, and we have that vertical asymptote that exists right here on the axis. So the only thing we can put into this fraction is what happens on the positive side of the vertical asymptote. Our range, of course, is negative infinity to positive infinity. Everything can come out. And that vertical asymptote is going to be a vertical line. Remember about our vux, a vertical line with an undefined slope and an x in the equation. And this h is going to tell us how far that graph shifts left or right. And remember, it's naturally negative. So whatever h value we see there, in that negative expression is going to be how our graph moves. All right, let's talk about a few. So when I look at this first one, my first thing I see is that it's definitely a reflection. And that negative sign makes it easy for me to recognize that this graph is going to be flipped. So if I think about this, it's going to be the opposite of everything. So we're going to go ahead and understand that reflection. All right, next up, I'm going to see that this graph has a +3, which means that this graph moves to the left 3. So when I look at what that means that my asymptote is going to exist at 3 to the left. That's where my asymptote is. All right, let's take a look at this next one. So I can see that 1/3 represents definitely a compression because of that fraction. I recognize that this common log is going to be smooshed, and guess what? It's going to go up by 1. If I look at this next one, because this value is greater than 1, it's going to represent a stretch. This +2 is going to move my graph to the left 2, and this -1 is going to move my graph down 1. Okay, so now we're going to actually start graphing these, and we definitely want to make sure that we use our graphing calculator as a resource. So we can look first at the transformation. It's our common log, and it's going to be +1. So we're going to have a vertical movement up 1. Because my graph does not go left or right, my domain is going to be from 0 to infinity. My range is going to be everything from -infinity to +infinity. When I talk about my asymptote, it's going to be that vertical line still at x is equal to 0 because my graph did not go left or right. So I know my asymptote is going to exist right here. So when I look at the parent function of a graph, I know that anything to 0 power is 1. Now I know that that graph is then going to be transferred up by 1. I know this is going to represent my asymptote, so I know this is going to snuggle up to and never reach. But I might want to refer to the graphing calculator to see if there's any other friendly numbers that can help me with that second part. So I'll go ahead and I'll type in our log of x, and that +1 is outside of the x parentheses, which means that that whole graph just moves up. Now here's an important thing. When we look at these graphs, you don't see the tail, but we know it's there. So with a log graph, we know that this goes all the way down, and you can verify that by looking at your graphing calculator. Okay, this should make sense to you. You can't have a negative x value. There's where our asymptote is, and we can see our 1, 1. Now when we look, we can see lots of decimals because it grows ever so slowly. But at 10, I have an output of 2. So my graph is increasing just slowly, 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 slowly as I go on up. So my log graph is going to look something like that. Okay? All right. Now, beware, if you graph logs in the calculator, it appears as if it stops, like we just saw, but it does not. The graph keeps going along the vertical asymptote. So we want to make sure that we, number 1, draw your asymptote, and number 2, keep that graph going along that log. Okay, here we have, let's talk about the transformations first of where this graph is going. Because I see a +1, I know that this graph is going to move to the left 1, and I know that it's going to move down 2. So if I talk about my asymptote, instead of my asymptote being along my y-axis, it's now going to be to the left 1. This point that I know of, over 0 or over 1 up 0, is now going to be to the left 1 and down 2. So I know my graph is going to continue on down this asymptote. I'm going to go to the calculator and look at and see if I can find another point that I can use to graph. So I'll go ahead and enter in the log of, and keep in mind x plus 1 is inside of the parentheses, and then down 2 is outside of the parentheses. so I can see my graph. Again, I know the tail is there even though I can't see it. I'm going to go to my table of values, and I'll go ahead and I'll look and see how quickly this graph is growing. Over 0, down 2, that was my first point that I graphed. Now let's see if there's another easy point for me to graph. 9, negative 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 1. So you can see this graph does not grow quickly at all. It takes a very long time, but it is going to continue growing up and up and up. So I will at some point eventually reach an output of infinity. It's just going to take me a very long time to get there. All right, domain. Remember, I can now snuggle up to negative 1. So that's going to be where I start and I stop at infinity. And my range is going to, of course, be all real numbers. Everything from the negative on up is just going to take a long time to get there. My asymptote is x is equal to negative 1. All right, so we don't have necessarily a homework assignment for this, just more practice. So this will be the end of the notes page, and then the second part is going to be, the second video is going to be more practice. So review how you're doing, and then come on in and we'll practice. We've got about, I don't know, 7 more graphs for you to do in the next video. All right. Good job, everybody.